Thank you to the organizers. So we'll talk today about a work that I did with Generative, and it is about multi-ground partition and character formulas. So the full article, you can find it in the full article with the same title in Advanced in Mathematics and with this exact reference. So I'll try to be very light for this last talk. So if you have to understand something, is it just this slide that I put on the first position? So what do we compute exactly? So we compute character of standard modules. So standard modules, there are some kind of representation in the for affine Lie algebra. So it's not the group algebra, the group Lie group algebra, but it's affine Lie group algebra. Affine Lie algebra. Sorry. So what are the existing methods to compute these characters? So the main formula that we know is the Velka character formula. And the thing about this formula is that when you have the character, at first it's a sum of exponential of what we call the weights. And so you have a sum with positive coefficient. And in this formula of Velka, we do not have an obvious fact that the coefficients are all non-negative. But there's a way to retrieve this fact. It's by doing what we call the principal specialization. So the principal specialization is a kind of transformation, but when we do this transformation, there is a lot of data, a lot of variable that we transform into one single variable. So there's a lot of information that we lost by doing this, but we obtain a product, which is really nice. And there are also some other methods. So what we call the vectors operator method. It permits to have what we call forbidden pattern. So you express so you have a kind of base in the character that you want to express in different ways, and via the vectors operator you can express this as some basis for where we do not have some forbidden patterns. And why is this interesting? It's because by doing these two methods, we have what we call we can have what we call Roger-Ramanujan type identities. So yes. So for the product side of the Roger-Ramanujan type identity, you can have it by using the principal specialization, and the sum side is obtained by doing the vectors operator. So what we have as another method, so what we are interested in is the method called the perfect crystals, and a formula related to it, which is the KMN square character formulas. So this is obtained by doing some sum over what we call the lambda path. So we'll briefly introduce this later. And what we bring to the table, what we add is that we make a bijection between this lambda path and what we introduce as a multi-ground partition. And by doing this, we simply express the character as a generating function of multi-ground partition. So this is what you have to you have to retain for this talk. So I will now introduce what is a multi-ground partition. But first, what is a partition? So a partition in the sense of integer partition. A partition is a non-increasing finite sequence of positive integers. So we have example 4, 3, 1, 1, and the sequence 1, 1, 1, 5 times. So what we study in our paper is something slightly different. So for that, we have to introduce a set of what we call a set of color. And we suppose that the integers occur in these colors in the set C. And we also add a binary relation on the set of colored integers. So an example here is that we take a set with 2 elements, and this relation is in order on the set of color integers in such a way that we have that 1 C2 is always greater than 1 C2, and is greater than 1 C1, greater than 1 C1, and so on, and will decrease in size of the integer. So by introducing this definition, the color, the notion of color integers and the binary relation, what we have is that we slightly modify this definition by doing this. So what we call a generalized color partition, so according to the relation, the binary relation that we introduced there, is a well-ordered finite sequence of colored integers according to the relation. So you have to take a finite sequence, and which is well-ranged according to the relation that we have here. So for example, with this order, which is a relation, we can have that the sequence 3C1, 3C1, 2C2, 2C1 is a generalized partition according to our order, but not 2C1 to C2 because they are not well ordered. So now, what is a multi-ground partition? So for that, we have to make an additional assumption. So you have a set of color, the integers colored, and the relation. And you suppose that you have T colors such that when you take these T integers color, which are unique, you have the sum of the integers, which is 0, and it's a kind of circle. They are well ordered, but it's a kind of circle that you obtain by doing this comparison. Okay, so the multi-ground partition, what is this? With ground CG0, CG T minus 1, and with the relation that we defined above. It's a non-empty generalized color partition such that the T last integers are what we have in our assumption, and we have the condition that the T integers before this T last integer they form a different sequence. So because we do not want to repeat this sequence at the end of the partition. Okay, so an example for the multi-ground partition. So you consider these matrices, and you suppose that when you have 3 colors, and you suppose that 2 elements are well ordered if the difference between the integers is greater than the quotient in these matrices. So these matrices is, so the B is for the row, and the B prime is for the column. And by doing this, when you choose G, so the 2 color to be C1 and C3, but you must have that the integers must be -1 and 1 and -1, and you have the following allowed multi-ground partition, and this one is not. These 2 ones are not allowed because here there is a repetition, and here we do not have that the difference between these 2 is less than what we have in the matrices, which is 2. So now if you want to take a nap, this is the time for the three next slides, because we'll briefly talk about what is a partition, a perfect crystal, and what is the KMN character formula. So it's not a definition, it's just an enumeration of what these notions are. So we have the perfect crystal. We take G to be an affine Moody algebra, and you have what we call the simple positive root, and also the null root, which is a sum of the simple positive roots. And then we also have what we call a dominant weights with a level L, and you have the notion of crystal of level L, which was introduced by Kashiwara and his co-authors, and the notion of energy function on what we call the tensor product. So all these notions, I won't detail them. I'll just mention them because they're what matters here is the combinatorial interpretation in terms of multi-grounds. And for such crystal, and such dominant weight, you have what we call the ground state path, which is a particular sequence. Here is written as a infinite product of tensor. But what you have to understand is that this sequence is periodic. And in particular, what we call the lambda path. So it's a sequence when you take the element in your crystal, and it has to be equal to, starting from a point, it has to be equal to the ground state path. Okay. So the KMN character formula. So what is the KMN square for? So it's 6 authors, and two of them have the first name beginning by K and M and N. But it's better than that, it's the 2 first letters of each name. So that's quite interesting. Maybe we can rename it. And the KMN crystal-based character formula state that when you have when you want to compute the character of the standard model, so this is what we which is what it's called irreducible high test weight UQG at module. So this is what we call the weights. So this is this sum which depend on what is a weight of an element of the crystal, and which also depend on the energy function. And the character is defined by this sum over the lambda path. So this notation is for the lambda path. I had to change it. Sorry for that I keep the notation there. So starting from this formula, we say that so the formula for the weights was really close to some size of partitions. So in what we call color partition, there is a way to have something similar, but it's not very similar because of this difference, which happen to be different at each step, at each G. So we had to, what we said, we normalize the energy function. So we take a perfect crystal, the level L dominant weight with ground state path, and this time the period is T. It's T, sorry. And G an energy function. And then we normalize the energy function. So we take the function and we subtract this means over the period. And again, we add another assumption that we take a D, which is a suitable divisor of 2, such as these 2 values are always integers. So with this assumption, we have that by considering so the set of color to be the set indexes by the crystal, and the relation defining by this difference according to our normalized energy function. We have that the multisets ground partition according to this relation is the set of non-generalized color partition, which end by these t color integers in such a way that we have this relation that we have in the definition of multi-ground partition. So the t integers, color integers before the t last one must define a different sequence, and you have the exact value of what uk must be for k from 0 to t minus 1. And with this definition, you had another assumption to the set to be that we consider is the multi-ground partition with our ground, say G0 and say so on, and say G t minus 1, and the relation that we defined in the previous slide. And the two additional conditions are that first one, the number of the part are the element that compose our partition. So the number of parts must be a multiple of t, and the difference between two consecutive parts it's not a multiplicative. The difference between the two consecutive parts minus this element. So there is a mistake here. It's not this difference, but this difference minus this expression must be a multiple of d. And with these two additional conditions, you have that to compute the character of our standard module is just to compute is equivalent to compute computing the generative function of this set of multi-ground partition, and you have a factor 1 over qd, which is what we call the Computational symbol. So it's an infinite product, so which is not relevant to define here, but it's express some partition. And this CP, how many do you have? 5. Okay, I think it's quite plenty. So the CP is for the product of the color that appear in the partition, and this symbol represents what we call the size of the partitions, which is the sum of the integers that compose the partition. So this theorem is really a generic method, because it's whenever you have a type, whenever you have the crystal of a certain level, you can just build a suitable set of multi-ground partition to have the character. So we take the example with the level 1 standard module of the Lie algebra A2 minus 1 power of 2 for n greater than 2, and you have this nice formula with there's a change of variable. So this is a product of Q series of a Q-Poisson symbol, and here the E, this operator is just the mean of the function, and the function where we change all the parameters C, the color C, by the opposites, and you have this nice formula. So how do you find this formula? Simply you take the crystal. So this is something which is in the literature. So you have many study of what is the perfect crystal for the classical type. So all we have to do, we do not have to do the algebraic study. We just have to take what is existing, and then we just interpret it in terms of multi-ground partition. And you have so this perfect crystal for the type A2 minus 1, 2 for the level 1, and there is only two level 1 weights for this type, which are lambda 0 and lambda 1, and these are the two corresponding lambda path. And the energy function is given by these matrices. So in these matrices, you have to understand that what I say H B1 product B2, you read the B1 according to the column and the B2 according to the row. And for example, here the one overline is this one. And with this, for the character of the lambda, the character for the lambda 0 standard module, you have so this interlacing sequence of overline 1 and 1 as the ground state path. And for this value of d, small d, capital D, small d, and t, you obtain that u0 and equal -1 and u1 is equal to 1. And you have the integers that you obtain are the odd color integers with our set of color and with this particular partial order. In particular, why you have these two are not ordered, because there is an interlacing sequence. They can form an interlacing sequence of integers. So you have 2k plus 1 c1, which is less than 2k minus 1 c overline 1, and so on and so on and so on. And by doing this, when you try to compute the multi-ground partition, the generative function of this multi-ground partition, you obtain this infinite product. And by applying the formula, you retrieve the theorem that we have at the beginning of this session. And we do the same thing for lambda 1, which gives something slightly different. Here we have one overlay 1 and so on. And for the same value of d, capital D, small d, and t, we have these two elements. So before we had -1 and 1. Here we have the opposite, is 1 and -1, and the generative function is slightly different for this one. So I will just end with a last slide. So what we have done so far is that we use our method to compute the character for the standard level 1 modules for this type. And we retrieve some classical formula given by Wakimoto for also these two type A2 n power 2 for n greater than 2, and dn plus 1, 2 for n greater than 3. And we also compute the character for the type A11, which is something which is really well studied, because for example, for the level 3, we retrieve the Roger-Ramanujan type, Roger-Ramanujan, not Roger-Ramanujan, but Roger-Ramanujan times a Q series. And what we obtain also is a identity with absolute value. So the energy, the relation that we had on color partition, on color integers, were defined by an absolute value according to the color we had. And what should be done is just to compute for the type CN1. So this is an ongoing work. So it is partially done, and to be crazy, you have to compute for, because the formula work for every level, all level of scalar type. So you want to apply this to compute all the standard modules. Thank you.
Any questions? Yes.
So if I taking a guess a little bit, you're using one particular realization, one very particular perfect crystal for
Right,
each
yes.
type. What happens when you change to some of the other perfect crystals?
No, the formula is for any perfect crystal of a certain level. So but we will have a different multi-ground partition. But at the end, the character is unique. So you have a different ways to express the same character as generative function of multi-ground partition.
So you basically understand the different types of how your combinatorics change when you change your representation. Yeah. Maybe I can ask a quick second question. What happened? Do you see rank level duality playing a role or giving you some identities?
For the type A n-1, we had this. So you try to understand how the duality affects our generative function. It happens that in the generative function, what we have, there is a kind of trick such that you have two colors which become inverse each other. So this is why the duality intervened from this type. So for the other, we do not focus on this, but there is a kind of inverse that occur in our formula. Maybe that can explain the duality.
Are there any further questions? No, if not, let's thank
you,
Isaac and all the speakers in this session.